In this live demonstration, we're going to create a program that simulates playing a game of casino craps. Now, on the slide, I have some of the basic rules of casino craps. We are going to be only simulating winning or losing when we are playing the pass line in casino craps, which is kind of the most basic bet we can make. There's a lot of other bets, some more exotic bets we can make on what the actual dice roll is going to be, or things like that. We're not going to take that into account, just the most basic version of this. Okay, so basically this is a casino game which simulation and random numbers lend themselves really nicely to, since most things in the casino are going to have random outcomes into them and they're not really skill-based. So here we're going to, when we play a game, we're going to roll a pair of dice and we're going to add their numbers together. So on the very first roll in a game of casino craps, which is called the come out roll, we're going to roll the dice. If the sum is a 7 or 11, we win. And if the sum is a 2, a 3, or a 12, we lose right away. And that's called crapping out. All right, so on that first roll, we can win or we can lose immediately. Otherwise, if we roll any other sum, so 4, 5, 6, 8, 9, 10, if we roll one of those, then we establish what's called the point. And what we're going to do is we're going to keep rolling the dice over and over again until we roll a 7 or until we hit the point. So if we roll a 7 first, then we are going to lose. If we hit the point, or roll that established number before we roll a 7, we're going to win. All right, so we're going to, in this round, we're going to win or lose. So what we're going to look at is, through simulation, what is the probability that we win, either by rolling a 7 or 11 on the come out or hitting our point before a 7 in subsequent rolls. And we're going to be assuming that in the actual casino, we're going to have a pair of fair dice. So we're going to have an equal probability of, on a single die, rolling a 1, 2, 3, 4, 5, or 6. And we'll carry that over through to our simulation as we're going through this. Now, because every time we roll the dice, we're going to presume that it's random, what numbers are going to come up. This is going to lend itself to a Monte Carlo simulation, because as soon as we pick up those dice, it's random what we are going to throw. So a Monte Carlo simulation of repeating this game over and over and over again is going to allow us to establish the probability that on any one game of this, we're going to win or lose by repeating it over and over again. And we're going to confirm that we have simulated it enough by making a convergence plot in this. All right, so I'm going to start looking at the code now. So just as a reminder, this is a live session. I've not solved this problem before, so you're going to be able to see kind of my process in putting together a program, testing the program, and verifying that it works as I go through it. I have already, though, copied and pasted some of the rules here of just the basic pass line bet that we are going to be simulating and testing here. Okay, so always we are going to be making a first roll. We have to roll the dice at least once, but there are different rules the first time we roll the dice versus if we have to roll the dice subsequent times. So we want to keep that in mind. All right, so I have my initialization here. I'm going to clear all my variables, close all my windows, clear the screen every time just to make sure we have a fresh slate. Now, eventually we do need to do a Monte Carlo simulation, because we don't want to just run this one time, because then we would think, oh, well, we won, so 100% of the time we win. No, we're using random numbers, and anytime we're doing a simulation that involves random numbers, we need to keep repeating it in something like a Monte Carlo simulation so that we get an idea of the probability of any one time what the value is we're going to get, or in this case, is it a success or is it a failure? All right, so I'm going to start by just getting this to work once. So simulating one game of craps, and I'm able to run that manually. Once I know that's working, then I'm going to build the Monte Carlo simulation around it so that I can automatically repeat this many, many times until we have run it enough times that we have a good sense of how often are we going to win this game if we bet the pass line, which is what we are going to be simulating here. All right, so we must run this, roll the dice at least one time. But again, we have this difference of the first time we roll it versus all subsequent times, because the first time we roll it, we want a 7 or 11 to win. But if we get a 2, 3, or 12, we are going to lose. But all subsequent times we roll the dice, if we have to, then it's going to be slightly different rules. So I'm going to set this up first, just simulating the first roll of the dice. All right, I'm going to call this, I guess I'll call it roll here, is going to be, now each die is, we can only have a 1, 2, 3, 4, 5, or 6. We have these discrete values here, and there's going to be 2 of them. So the rolling of one die, I'm going to simulate with rand I. I want a random integer from 1 to 6. So if I just keep doing this, we see that if I keep running it with evaluate, I'm doing evaluate selection here over and over again. That every time I do it, I'm getting a random number, 1, 2, 3, 4, 5, or 6, and it's going to be an 1/6 chance of a 1, a 2, a 3, 4, 5, or 6 each time. So randi is already designed that way. But I am rolling 2 dice. So I want, copy this up here, to not roll 1, but 2. So this tells me the first number is what, there's different ways I can do this, but if I just put one number here, it's going to be a random integer from 1 to the number I put here, in this case 6. And then how many rows, how many columns I want is the 2 and the 1. So now this is simulating rolling 2 dice. So this is here, I rolled a 2 on one die and a 1 on the other. A 1 on one, a 5 on the other. So I can keep randomly rolling 2 dice here. So keep in mind, when we roll 2 dice and we add the values together, we are not getting, each die individually has a uniform probability, an equal chance that is, of a 1, 2, 3, 4, 5, or 6. But the sum of 2 dice is not a uniform probability. We are going to most likely get a 7 and then least likely get a 1 or a 12. Because there's a lot of ways we can roll a 7, a 3 and a 4, or a 5 and a 2, a 6 and a 1. But there's only one way to roll a 2, and that's a 1 on each die. Only one way to roll a 12, a 6 on each die. So what we really care about, though, in this game, at least when we're just playing the pass line, is the sum of the dice. Again, there's other bets where we are betting on, are we rolling 2 3s or 2 4s? We're not worrying ourselves with that, so we can ignore what the individual dice are. So I can roll the 2 dice, and really, again, I care about in this simulation, when we add them together, what is their sum. So I can sum them, and now if I keep running this, if we see the numbers that come up, we're getting numbers closer to 7 more frequently, then we get numbers further from 7, like 2 and 12. I'm not going to look at the histogram for this, that's a separate exercise, but this is going to give us the proper probability of, when we roll 2 dice, what their values are. So I'm going to call that roll. So this is going to be first roll, or that is the come out roll in the lingo of casino craps. Okay, so that is that first roll, and we're going to get what the sum of the 2 dice are. So again, all these different numbers it can be. Now the rule on the come out roll is we're going to win if it's a 7 or an 11. So if roll equals 7 or roll equals 11, so this is a winning roll, we want to do something. I'm going to say win equals 1. All we are going to keep track of is, did we win the game or did we lose the game? So on the come out roll, if we roll a 7 or 11, we instantly win. So I'll set this win equal to 1. So the 1 is just, win is just going to be binary. 1 is going to be winning the game. 0 will be losing the game. Else if, so we are going to lose instantly if it's a 2, a 3, or a 12. So 2, or roll is 3, or roll is 12. Right away, we'll set win to 0 because we instantly lose. So the way in my head I'm going to program this one, we'll see how it develops in a minute. I've been able to here simulate that the first roll. So let's just see what happens here. If I press go, I rolled a 10. Notice that win is not set in the workspace. If I run this again, okay, my roll was a 7, win was set to 1. Let's see one where we lose. We rolled a 3. That on the come out sets us win equals to 0. So we have the first roll, at least if it's a 2, 3, 12, 7, 11, this is working. Oops, and I have to fix that because it's 7 or 11 is a winning roll. All right, so now we, again, can keep running this a couple times. So 12, we lost on the come out. A 6, well, we would have to roll subsequently. So we'll work on that from here. Okay, so we have the come out roll set. Now what we have to look at is what if we hit a point and now we have to go into this second phase where we have to keep rolling the dice until we hit our point or we get a 7, whichever comes first, and then that will tell us, in that case, do we win or do we lose? So since we're going to potentially keep rolling the die, this is going to lend itself to a loop of some sort. Oh, and going back, even the way this is stated, I took this statement from Wikipedia, the rules here. Notice the word if in there. Well, that translates directly to we need a conditional if statement in our program. Now, the next part is when we are rolling for the point, we are going to be rolling until some outcome, until we hit the point or until we roll a 7. If we here do something until or do something while, that is a clue that we probably want to use a loop, and specifically if we hear while or until, that's a clue that probably a while loop is going to be better for us than a for loop. Now I don't want to use a for loop here probably because I don't know how many times I'm going to have to keep rolling the dice. I could hit the point the first roll. I could not roll a 7 or a point for a dozen or 30 rolls possibly and have to keep rolling over and over again. So a for loop is not going to be great. I don't know up front how many times I'm going to have to roll it. So I'm going to do a while loop here. Now this is a case where, one, if I rolled that 7, 11, 2, 3, 12 on the come out, I don't need to roll the dice anymore. The game is over. Or the round is over. So I don't need to re-roll at all. So I actually want to skip over this while loop if that was the case. And I want to signal that if I do have to hit my point or hit a 7 afterwards, that the loop knows to stop. So I'm going to use here a flag. Right? So you saw me do this in some other videos. The flag is just going to be this binary 1 or 0 that tells me, that just indicates should I do something or not. Right, so I'm going to set flag equal to 1 here. Now, again, I don't want to go into this loop if I already won, if I hit a 7 or 11. So what I'm going to do is set flag to 0 if the game is already over before I get to this while loop. So the game is over whether I win or lose on that come out. But I'm going to initialize flag to 1. Right, so again, what we see here, flag is going to be initially 1. If the game is over after the come out, I'm going to set flag to 0. And when we come down to this while loop down here, flag will be set to 0 only if the game is already over. So this while loop won't even trigger in that case. But like here, if I rolled a 6, well, it doesn't hit the first if statement. It doesn't hit the else if statement. So flag is never changed from 1. It remains 1. So I will enter this while loop. Now I could have also done this maybe with an else statement here. But then I'm going to have like a while loop inside an else statement. That's not a huge deal. That would be another way to do this. I'm going to do it otherwise using this flag statement because of the way there's other things that can set the flag to 0. And I think it'll be easier to do it this way, but there are definitely alternate ways to do this. Okay, so if we roll a 6, we want to enter, for example, we want to enter this second phase where we are going to keep rolling. And actually, I am going to set here for later use, I'll call this point equals roll. because I want to remember what's that number I need to roll again in order for the game to be over. All right, so I'm going to save the point from the first roll. All right, so while flag is 1, I'm going to keep re-rolling the dice. So I actually can just copy this right into here. All right, so this is going to be my roll for point segment of the code. All right, so I'm going to re-roll the dice, and now I want to check this roll. So I can say, all right, we'll win if roll equals point. Remember, the point is only established from the first roll. So I re-roll the dice, and I'm going to check, is it equal to the point I set in 40? If so, that's another win condition. So win I set to 1. And also this tells me to stop rolling the dice. The game is over. So also here, I'll set the flag to 0. Else if roll is 7. So remember here, in this second phase, once we've established the point, if we hit the point before we roll a 7, we win. If we roll and hit a 7 first, we're going to lose, or 7 out. So we're going to check our roll. Is it equal to our point? Is it equal to 7? Well, then win is 0. And also, we need to stop rolling the dice. And here, if we roll anything that's not a point or a 7, we could put an else here, but it's not going to do anything. If we roll something that's not a point or a 7, well, then we're going to go to the end of this loop. Flag will still be true, and we're going to re-roll the dice. And then we're going to check again, is it the point or the 7? If not, we're going to re-roll. So the way that I set this up with the flag here is the flag is set to 0 once the game is over. And if the game is not over, then we're going to keep re-rolling the dice in this while loop. Make sure everything is... All right, so that's really the basic mechanics of this, is we roll the come out, and then we keep rolling for point after that, if all we're trying to do is establish, are we winning or losing this pass line. So again, winning is set to 1, and losing, the win variable, is going to be set to 0. All right, now let me roll this. All right, so in this case, we have a lot more going on. We're not seeing all the details of what's happening here, but in this case, we must have rolled a 9 on the come out, and we rolled a 9 in this rolling for point, and we won. Here, it looks like we probably rolled a 7 on the come out, and we won. Looking for one where we lose. All right, so here it looks like what happened was we rolled for point and it was 6. We got into this loop down here and we rolled a 7 before we rolled our point. All right, so this is where, just to make sure it's working properly at this point, I'm going to set a breakpoint and we can step through this and kind of follow the program. What is it doing with this step? Okay, so we're initializing the flag. So we roll the dice. We rolled a 7 on the come out. All right, so we enter this first thing. Win is set to 1, flag is set to 0. We keep going. We establish the point. It's actually not going to matter in this case. We already won. The flag is set to 0, so we skip over this while loop, and we're done. Let me try this again. Okay, so flag is initialized to 1. We roll the dice. We got a 7 again. That's not very interesting. Let's see one where something else happens. Okay, we roll the 6. On the come out. So let's just see what happens. Is it a 7 or 11? Nope. Okay, it skips it. Is it a 2, a 3, or 12? Nope, it should skip that. All right, it establishes the point, and we see point is set to 6. All right, so now we're going to keep re-rolling. All right, so we should enter this loop, and we do. We re-roll the dice. We got an 11. In this phase, an 11 is nothing. We just kind of ignore it. So neither of these if statements triggers. So we go back and we re-roll the dice. It's a 6. So we rolled our point, so we should enter this if loop, this if block, and we do. So win is set to 1, flag is set to 0, which means stop rolling. So we exit out of the while loop because we're done, and we see win was set to 1. All right, so we explored a couple different possibilities when we rolled. I'm going to get rid of this breakpoint here. So now our simulation works for a single game of casino craps. So again, if I keep running this, win is sometimes 1, win is sometimes 0. A lot of different things can happen. But what we want to do now is establish what's the probability that when we play a game, we bet the pass line, we're going to win. Well, we have to do this a lot of times to know how that's going to work. So around this whole thing, I'm going to make my Monte Carlo simulation. Right, so I'm going to make something called SAMPS. I'll start it small with just 10 samples. Just to make sure it works, I'm going to start small before I ramp it up. Right, so around this whole thing, I want to repeat this whole game SAMPS times. So initially 10 times. Right, so let me do a smart indent. So all this game is going to re-happen over and over again. Initially only 10 times, but I'll scale that up higher. Now, everything is going to reset. The flag is going to reset every time. I'm going to do the come out again every time. And really what I want to record inside this outer loop is, did I win or lose? Right, so I'm going to make something called I'll call it win master here, and this will keep track of my wins and losses on any individual game, but in the end I'll have this list of wins and losses for all initially 10 games, but then 1,000 or 1,000,000 games. So win master, you notice here, is going to be indexed. So on the kth game I'm playing, or in the kth universe this is taking place, I'm recording, was this game a win or a loss? Right, so this is the only thing that will really be preserved once the loop is over, is this list of win master. And notice here it's underlined. It's telling me that there it is. Appears to change size every loop. I want to, anything that is indexed like this, like a vector that I'm going to be filling in, I do want to pre-allocate outside the loop. Right, so I'm going to initialize this as zeros, the length of SAMPS. So when SAMPS is 10, this should be a list of 10 numbers, zeros, initially all zeros, but I'm going to fill in their actual values as I go through this list. Right, so always want to pre-allocate here. All right, so I'm just initially going to do this for 10 times, just so we can see what this looks like. Right, and if we look at win master, right, again, this is the whole history. This is on the first simulation, we won, we lost, we won, lost, win, loss. All right, so what we can look at is, for at least these 10 games, what was the probability that we won? Now this is set up nicely because we have ones and zeros, so really we can just look at the average or the mean of this vector, and that tells us our win probability, or the number of simulations that ended up in a win. If we run that, it comes out to 0.5. But the problem is, if I keep running this, my average is changing. It's hovering kind of near 0.5, but it's not steady there. And what that is telling me, and we'll see graphically, is that I'm not running enough simulations for this mean to be reliable, for this calculation to give me an accurate estimate. We notice the 1 digit of accuracy we have keeps changing. All right, so what we want to do here is graphically look at a convergence plot to see, have we run this enough times? Right, so I am going to make this cum sum of win master. Right, so this is going to add it as we go, as we saw in some of the other demonstrations here. And I'm going to divide that by 1 to SAMPS. Okay, the problem is this is a row vector and this is a column vector, so I'll make this also a column vector by doing that transpose. Oh, that's why I want a dot division. All right, there we go. So now what this line of code is doing is it is calculating kind of our running average. So after the first game, if we just look at win master, all right, so we won, lost. Now let's look at this. All right, so on average, we won 100% of the games, 100% of the games. Then we have our first loss. So this is saying, okay, 2/3 of the games we won, 3/4 of the games. So every time we add a new game, it recalculates the mean. And using basically the law of large numbers here, once we have enough games played, this value should converge to one number, and we're going to also be able to see that graphically. So what I can do here is do a semi-log x plot of that value. And what we're going to see, an indicator that we've run this enough times, is that our value of this cum sum should level off. And we see here it certainly has not. And let me put a grid on so we can see a little bit better. I'll put in an X label, so N will be the number of samples or the number of times we played the game, and our Y will be our win percentage. So now if I run this, again, 10 times, not enough data here. We have not leveled off. It's telling us we won 60% of the time. I guess really I'll do 100 times this so we can see a percentage. All right, so again, this time it says 70% after 10 runs. If I run it again, I'm only at 40%. It's all over the place. All right, so what I want to do here is I want to up the number of samples. So instead of only running this 10 times, let's run this 100 times. All right, so we run it 100 times here. We see we are, I would say, still not flat over here. We're still, it looks like we're still declining. We go up again, I'll run it 1,000 times. Right, so we see that that number is, using law of large numbers, we're closing in kind of on 50% here. I would say even with 1,000, we're probably still not leveled off. It's better for the most part to do this more than we might need. There's the time is the only, the time it takes is the downside of kind of running this too many times. But graphically, we're really going to see now it's a lot more clear on this semi-log plot. I'll make it even bigger here. That it's starting to, definitely by here, by, let me mark this point. By the time we get, again, just by I here, to about 50,000 repeats, that we are fairly leveled off, although it is still kind of changing its value a little bit as we're going. But we see the variability is much bigger back here until we get to like 1,000, 10,000 repeats, where now the change in its value is getting smaller and smaller. General rule of thumb is every time we dectuple the number of samples we run, we gain one more decimal place of precision. Yeah, that's a rough estimate, but that's somewhat true in general. So if I dectuple this, so I go from 100,000 to 1,000,000 samples, I should get even more precision in what my estimate is going to be as to how often I'm going to win. So again, visually at least, we see we're like pretty level over here. I'll do one more just so we're sure. I'll run this 5,000,000 times, and then we're going to see it does level out. We can be pretty sure on our win percentage. All right, so we see the plot that comes up after running it 5,000,000 times. Let me tighten up this, do an axis tight here, so and just rerun the plot. All right, so we see it's really going to be flat here, making this even bigger, and we can see really the number's not changing as we add more and more samples once we run this like 5,000,000 times. So we run it 5,000,000 times, and we see that our win percentage is 49.34, so a little bit less than 50%. And actually, we see here the same number when I display, again, I'll do 100 times this just so we can see it as a percentage. So 49.34 about is our win percentage here. All right, so we've shown through this convergence plot that we have converged, and anytime we're doing simulations with random numbers, a convergence plot is key to making the argument that we've run this enough times that we can trust the data we get and the conclusion we're making. It's leveled off here. We could run it even more times, but it appears to be leveled off. And we saw that 49.34% of the time we win, the rest of the time we lose. Actually, from the casino's point of view, this is important. They don't want to run a game that they are going to lose more than 50% of the time. So we see in this game, just betting the pass line, we have a slightly less than 50% chance to win. So in this game, if we bet $5, we're going to win $5 only about 49.34% of the time. The casino is going to win our $5 the majority of the time. It is a pretty thin margin, but the more often we play this, the casino in the long run is going to make money, as they are going to be winning slightly over 50% of the time. So they are on average taking in slightly more money than they have to pay out, at least when you bet the pass line. So if you look at the probabilities for the other types of bets you can make, I think in casino craps, probably the one that's closest to a 50% is going to be the pass line. A lot of the other bets you can make are going to have even worse percentages that are even more in favor for the casino. So in this problem, the methodology for solving it, we wanted to start small. So don't worry about repeating it yet. Let's just get it to work for a single iteration of this game or iteration of this simulation. So that's where we started, making sure it worked properly. Then kind of the easy part is just building the Monte Carlo around it. So all that took was on the outside, this for loop that's going to simulate it the number of times that we specify. We want to start that number, the number of repetitions, fairly small, just to make sure it's working the way we think it is. And then graphically, we want to make our convergence plot. So that's what we're doing here at the end. Once we've graphically determined that, yes, we've run this enough times, we have convergence, we have that horizontal line happening as we take the running mean of some value. Once it's kind of flatlined there, that tells us we've run it enough times, and the value at the end is a value that we can trust. So in this case, after running it 5 million times, that value of winning about 49.34% of the time, I would say that if we did everything else right, we've run this enough times that we can trust that as our outcome.